Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Abdul Halim here and welcome to my channel. In this video, we are going to explain four formula related to geometric sequence and series. Okay, for formula number one, that is finding the nth term of a geometric sequence. And then we are going also to talk about Sn, that is the partial sum of a geometric series. Now there is another version, that is formula number 3 of the same sum, that is the partial sum of the geometric series. Okay, another version, this formula number here, number 3, this is formula number 2. And lastly, we are going to explain about the infinite sum of a geometric series, okay, especially for the absolute value of r less than 1. For any sequence of number, we can represent the terms of the sequence as A1. That's for the first term, and then maybe we can write A2 for the second term. Then we can write A3, the third term. We have A4 for the fourth term. And then we have A to n minus 1 terms. This is the nth term, and maybe the sequence goes to infinity. Now for a geometric sequence, they have a very special characteristic, that is, okay, for any pair of terms in the sequence, okay, to find the next term, is, for example, to find A2, the previous term, that is A1, have to multiply by a very special number, that is what we call R. So A1 multiplied by R, we have A2. Okay, the same thing goes for any other pair, for example, like this one, A3 and A4. Now, to find the next term, that is, to find A4, what we have to do is, we have to multiply A3 multiplied by, again, the same number R. Now, for this pair, okay, to find the next term, that is for the nth term, we have to multiply the n minus 1 terms, we also have to multiply by that special number R. Now, that number R is called common ratio. Okay, sorry, common ratio. Now, that means if we divide, okay, for this first pair that we discussed just now. So if we divide the next term by the previous term, that is, if we divide A2 divide by A1, okay, we can get R. Okay, not only that, if we divide, okay, pair of A3 and A2, that is, if we divide A3 divided by A2, we also get the same number R. Okay, the next one, for example, A4 divided by A3, okay, we still get R also. That is, an, that is any value for n, divided by the previous term, that is an minus 1, also equal to R. Okay, because any geometric sequence, they have this special number R. Okay, now what is the value of R is depend on the sequence that is given to us, but it must be common, meaning must be the same, okay, across the sequence. The ratio must be the same number all the time. All right, so now let's write down the first term, that is, we have A1. Okay, to find A2, we already mentioned that to find A2 must be A1 multiplied by R, right? Okay, where A1 is the first term and R is the common ratio. Okay, to find A3 equal to, all right, the previous term, that is A2 multiplied by R. But A2 is equal to all this. Yes, now we are going to substitute equal to that. That is A1 R, we have to multiply by R. This is equal to, we have A1 R square. Now, let's do the same process for the next pair, that is A4, that is to find A4. Okay, A3 have to multiply by R, right? Now, A3 equal to this. Yeah, A3 equal to a1 r square have to multiply by r also, so this is equal to a1 r square multiplied by r is r cubed, right? Now let's do another one, that is, let's use a different color, that is a5 must be a4, okay, multiplied by r. Now this is a4 here, so I want to replace a4 by that is a1 r cubed multiplied by r. Now see here, we have r cubed and also we have 1 r to the power 1, so when we multiply we have to add the power, so we have a1 r to the power 4, because 3 plus 1 is equal to 4. Now can you see the pattern, okay, after doing some of these terms of the sequence, the relationship maybe we can recognize between, for example, this one a3 and a1 r square. Do you notice that, okay, this number 3 here and also this number 2 and this number 2, okay, this number 4 and this number 3, do you see the difference or the relationship between these two numbers? Okay, see here 5 there and we have 4 here. Can you guess what will be our next term? That is what is our terms number 6, that is what is a6, by looking at the pattern. Can you guess what will be the next term in terms of a1 and r? Yeah, of course we have to have a1, right? Because okay, all terms here they have a1, we have a1, and also we have a1, therefore a6 also have to have a1. Multiply by r, but r to power what? Yes, we have to subtract 1 from this number 6. You see here, we get 4 when we subtract 1 from 5, right? Here we have 3, subtract, okay, 1 from 4. So we have 6 here, we have to subtract 1 from 6. So therefore here we have to have r to the power 5, right? Now can we write one more terms, that's a6. Okay, a7 I mean, a7, that's equal to, must be a1 also. Now the power of r must be, okay, we have to subtract 1 from 7. Okay, that means the power for r in this case is r to the power 6. Now that's the same, I mean, we have to continue with the same pattern. By looking at the patterns, then we can write down whatever. For example, if we want to write down a10, can we write down what is the formula for a10? Must be a1 also. Okay, r, now what is the power of r? Must be 9. Yeah, must be 9, because 10 minus 1 is 9, right? Now can we continue the process and write down what is the nth term? I mean an, what is an equal to? Yeah, must be a1, have to have a1, because every terms previously they have a1, so for an also they have to have a1. Okay, the question is, what is the power of r? Now we have to subtract. Okay, we have to subtract 1 from n, right? So how to write it down? Yeah, must be to the power, r must be to the power n minus 1. Okay, this will be the formula to find the nth term for the geometric sequence. Now when we add the terms in the geometric sequence, that is a1, we add with a2, we add with a3, and so on, up to maybe a of n minus 1, maybe the last term will be an. Okay, when we add the terms in the geometric sequence, we call it geometric series, right? Okay, now we would like to find what is the formula for Sn. Okay, the formula for Sn. Sn is just the sum of the terms up to the nth term. Alright, and Sn is called, they have a name for it, we call it partial sum. Alright. Okay, so now we want to produce, or we want to derive the formula for Sn. Now this is the process that we have to do as follows. You can write, okay, Sn equal to the first term of geometric sequence, that is a1. The second term, I hope you still remember, that is a1r. Now the third term is a1 r square, okay, plus, now what is the nth term of a geometric sequence? That is a1 r to the power n minus 2, sorry, n minus 2. Now what is the nth term of a geometric sequence? I hope you still remember the formula for an, that is a1 r to the power n minus 1. Now let's call this equation as equation number 1. Okay, now what I want to do next is I want to multiply r, okay, I want to multiply by equation number 1. That is, I want to multiply r with this equation here, with this equation. Now what will be that equal to on the right hand side? Okay, on the left hand side, Sn multiplied by r will be r Sn. Now how about all the terms on the right hand side, okay, when we multiply each one of them by r? Now the first term, okay, let's do it one by one. Okay, what will be a1 when we multiply by r? What we have? Yeah, we have a1, we have a1r, right? Now for the second term, that is this term a1r multiplied by r, what happened? Yeah, we have a1 r square. So we have a1 r square. Now the third term, this third term will be a1 r cube, and so on. Okay, we can continue the process up to, now what will be a1 r to the power n minus 2 multiplied by r? Yeah, the power of r here, that is n minus 2, we have to subtract 1. So the power of r will be n minus 1. So for this term, it will be a1 r to the power n minus 1. Now what happened, okay, for the last term, that is a1 r to the power n minus 1 multiplied by r? Okay, the power of r will have to add 1. So n minus 1 plus 1. So 1 and negative 1 will cancel. The power of r, okay, will just be n. So the last term will be a1 r to the power n. Alright, now let's call this equation equation number 2. Okay, now we have two equations, and we would like to subtract equation number 1 from equation number 2. Okay, that's what we would like to do. That is, we want to do this. That is equation number 2 minus equation number 1. Okay, that is the equation in red minus equation in white. Yes, so what happened? On the left hand side, we have rsn minus sn. Okay, that will be the term on the left. Okay, let's write it down. Okay, so we have on the left will be rsn minus sn equal to, now for a1r, okay, for a1r we have a1r here, and also we have a1r there. Okay, when we subtract equation 1 from equation number 2, a1r minus a1r will cancel. So this term and that term will cancel. Okay, whenever we have the same term, it will cancel when we subtract. Yeah, so we have a1r square here, and also we have a1r square there. Okay, now let's continue, see whether we can cancel a1r3. Do we have a1r3 in equation number 1? The answer is yes, because it's somewhere here, but it is not written. It is there. So a1r cube, we have it, okay, somewhere here in between this plus 2 plus sign. So a1 r3 also will cancel. All the terms will cancel. Okay, all terms here will cancel because they have in both equations, including this one, that is a1 r to the power n minus 1. It also will cancel because it has, okay, a1 r to the power n minus 2, and a1 r to the power n minus 2 also in equation number 2. So this one also will cancel. Now how about this term? Okay, a1 r to the power n minus 1 also, yes, we have a1 r to the power n minus 1 in both equations. So this term also will cancel. Now how about this term? Okay, the last term in equation number 2, a1 r to the power n. Now, do we have that term in equation number 1? No, we don't have. Therefore, this one will stay, a1 r to the power n. So what's left after we do this operation, that is 2 minus 1? Okay, we have left on the right hand side only this term, that is a1, and a1 to the power, a1 multiplied by r to the power n. So what we have is, here we have, because the terms a1 we don't have here, so 0 minus a1 is negative a1. Okay, now the last term in equation number 2 we have plus a1 r to the power n. Okay, that's what we have after we do the subtraction. Equation number 2, equation number 1, subtract, right? The left hand side we have this, and the right hand side we have that. Okay, now let's rearrange the term on the right hand side. We have r Sn minus Sn equal to, I want to write down a1 r to the power n first, and then subtract a1. Now for the left hand side we have Sn, and also we have Sn here. Okay, Sn we have it in both terms, so we can factorize Sn. We left with r minus 1 over there equal to, now on the right hand side both term we have a1, so we can factorize a1. Now for the first term we left with rn, for the second term with 1, like this. Now we are interested to find Sn, so we have to divide by r minus 1. Divide by r minus 1 here, divide by r minus 1 on the right, on the left. So if we do that, then r minus 1 on the left will cancel. Alright, so we left with the terms on the right hand side. So now we have this Sn equal to a1 multiplied by r to the power n minus 1, okay, divide by r minus 1. But we have to make sure that the value of r must not equal to 1. Okay, we have to have that condition, because if we allow r equal to 1, then at the denominator we have r minus 1, that is 1 minus 1 is equal to 0. So dividing any number by 0 will be undefined, so we won't allow r equal to 1. So r must not equal to 1. So that is the formula to find the partial sum Sn, that is equal to a1 multiplied by r to the power n minus 1 divided by r minus 1, with the condition that r cannot be equal to 1. As we explained a few minutes ago, that if we write Sn, that is for the partial sum of geometric series like this, that is a1 plus a1r plus a1r square up to the last term is the nth term, that is a1, yeah, sorry, this is must have a1 multiplied by r to the power n minus 1. This last term is an. Alright, now, okay, last time we explained that, okay, this equation, now let's call equation, that one is equation number 1, as we did as before, call it 1, equation 1. Now if we multiply equation 1 by r, we have this r Sn on the left is equal to a1r, and so on, as we explained before. That is, the last term will be a, that is a1 there, sorry, a1 multiplied by r to the power n. Okay, we derive the last formula by doing this, that is 2 minus 1, right? Remember, we do equation minus 2 minus equation number 1. Okay, that's what we do, okay, in the previous explanation. But this time we are not going to do that. We are going the other way around. That is, this time what we are going to do is, okay, equation number 1, we want to subtract equation number 1, subtract equation number 2, like this. 1 minus 2, what happened? Alright, on the left hand side, this is equation number 1 on the top, and here at the bottom we have equation number 2. So on the left, if we subtract 2 from 1, so Sn minus Rsn. So that's what we have on the left hand side, okay, by using this color here. So we have Sn minus Rsn, that is equal to, right, as we explained in the previous what we call deriving the formula, we can cancel because we are doing subtraction. So if we have the same term, okay, the same thing, we can cancel, right? So we can cancel this time. We can cancel a1 because they have a1 also in equation number 2. Equation number 1, we have a1 r square, we have a1 r square also there. Okay, for a1 r3 also we have here, we have somewhere there, all the terms in between here will cancel. All right, now we come up to this term, that is a1 r to the power n minus 1, that is this term. Also they have somewhere here, so all these terms will cancel. Now we have a r to the power n minus 1, over here we have that one, and also we have in equation number 2, both of them we have in both equations, so we can cancel this term, right? So now what's left is a1 r to the power n. Okay, so what's left is, after we do all this cancellation, is that we have on the right hand side we have a1, okay, minus this last term, okay, a1 r to the power n. All right, so we get negative a1 r to the power n because this time equation number 1 minus equation number 2. This is our equation number 2. This equation number 2. All right, so on the right we have a1 minus a1 r to the power n. Now as we did before, we can factorize on the left hand side. We can factorize Sn, right? We can have 1 minus r there equal to, on the right hand side we have a1 here, and we have 1 minus r to the power n, like that. Okay, now we are going to divide both sides by 1 minus r. Over here also we want to divide by 1 minus r. So what happens if we do that? Then we can cancel 1 minus r, we can cancel 1 minus r. So we left with Sn equal to a1 1 minus r to the power n, okay, over 1 minus r. Okay, now in using this formula we have to be a little bit careful because we cannot have, okay, we won't allow r must not equal to 1. We won't allow r equal to 1 because when r equal to 1, the denominator will be equal to 0, and that will be undefined. So r must not equal to 1. So this is the second version of the formula for partial sum of the geometric series. All right, we can use this formula, this version, or the previous version, as we explained in the previous discussion. Either we can use this one or we can use that formula. Okay, both formula is is valid, and we can use either one of them to find the partial sum. Okay, only that we cannot have r equal to 1. Now we would like to discuss what happened when we want to add the sum, or we want to find the sum of the geometric series if the term is infinitely many. That is, we are looking for S infinity. Yeah, S infinity, like this. That is the sum of infinite geometric series. Okay, but before we do that, let's refer back to our Sn. Okay, now the first version of Sn is this. So we still remember the formula, that is Sn equal to a1 multiplied by r to the power n minus 1 divided by r minus 1. Okay, as long as r is not equal to 1, remember? Yes, now we would like to break down this equation on the right hand side, especially into two parts. Okay, first we have to multiply a1, okay, to the terms in the bracket, meaning to say open the bracket. So we have a1 multiplied by r to the power n minus, we have a1 there. Now divide by r minus 1, like this. Okay, so let's divide one by one by r minus 1. So we have a1 r to the power n over r minus 1 minus, we have a1 over r minus 1 like this. Alright, so now we are, okay, we would like to focus more on the first term, okay, on this term. What happened actually to this term, right? Because in this case, we want to see what happened when n approaching infinity, right? Because the terms in the sequence that we are adding is infinitely many, n is approaching infinity. Now, I would like to write it, okay, that particular terms over here. I want to copy and write it down here. A1 r to the power n divided by n minus 1. I want to investigate what happened to this part, to this component, okay, to this term when n is approaching infinity, when r is between -1 and 1. Okay, so we are looking for this term, what happened to it when r is between -1 and 1, and also when n is approaching infinity, what happened to r to the power n. Alright, so we see that when r is between -1 and 1 and r is approaching infinity, okay, this term will go to 0. This term will go to 0. Okay, let me write it down. For r between -1 and 1, okay, r to the power n will go to 0 as n approaching infinity. Alright, that is when n is approaching infinity. For this particular value of r that is between -1 and 1, r to the power n will go to 0. What that means is this term, this term here will go to 0. Alright, so now what we left with is only this term. That is, the answer is negative a1 over r minus 1, or it is equal to a1 over 1 minus r. Okay, provided that the value of r is between -1 and 1, or we say the absolute value of r must be less than 1. Okay, let us write down the equation one more time, the formula one more time, I mean. So we have s infinity, okay, equal to a1 over 1 minus r, okay, provided that the absolute value of r must be less than 1. We can also show the formula for s infinity by using the second version. That is, if we write down Sn, okay, equal to a1 multiplied by 1 minus r to the power n divided by 1 minus r. Okay, this is the second version of what we call the n's partial sum of geometric series, right? Now, with the condition that r cannot be equal to 1. Again, as we did before, we multiply a1, okay, with the terms in the bracket. We have a1 minus a1 r to the power n, all of it over 1 minus r, right? Now let's again break it down into two parts. That is, the first term will be a1 over 1 minus r minus a1 r to the power n over 1 minus r. Now, with the same argument as before, all right, this term will go to 0. Will go to 0. Okay, for r in between -1 and 1, all right, this term will go to 0. That is, r to the power n will go to 0 as n approaching infinity. All right, so when rn is equal to 0, therefore that means is this whole thing equal to 0, will go to 0. So what's left is we have a1 over 1 minus r. Now let's write down as infinity again. Okay, therefore we have this formula, that is, okay, the infinite sum of the geometric series is equal to a1 over 1 minus r, the same formula as we get before. Okay, provided that the value of r must be, the absolute value of r must be less than 1.